webinar in a series. It's connecting the dots, getting the most out of your CPU performance with data-oriented technology stack. It's a very important topic because DOTS is running more and more systems inside Unity, and it will be increasingly important to at least understand what is it about. And in this webinar, I'm going to give you a quick introduction to DOTS and ECS pattern based on two simple projects I'm going to show you. My name is Marek. I'm evangelist at Unity Technologies Singapore. And before I joined Unity, I was working as a game programmer. And I really wish that I had a technology like DOTS when I was a full-time gameplay programmer, because this opens like a new, really new possibilities for you. Okay, I can hear that everything is fine on YouTube. You can hear me on Zoom. If you want to ask any questions, there is a Q&A section on Zoom, and I'll be going through the Q&A section every once in a while. Unfortunately, you won't be able to ask questions on YouTube. On YouTube, we have only like a push, so you'll be only hearing and seeing what we have here, but you won't be able to ask questions. Only Zoom attendees can ask questions in the Q&A section. But after the webinar, I encourage you to visit our Discord channel. So Unity Southeast Asia, Australia, New Zealand, in our region, we have a Discord channel where we're going to have like a post-webinar discussion about DOTS. So if you couldn't ask any question here, you'll be able to ask it in the Discord. All right, so today I'm going to give you a quick introduction to DOTS and ECS pattern. Then we are going to go through a project, I call it like extremely efficient rotating cubes with ECS, because we are going to rotate quite a lot of game objects and move them around the scene. This is a very good exercise that allows you to better understand how what the DOTS and the ECS pattern is about. And then I'm going to show you another project I created. This is a formation movement with steering agent behavior. So here you can see that I can select different formations and I can move them around the scene, and later I'm going to add like the destruction to this example. And I think it really well demonstrates how you can create gameplay and different systems using DOTS. Alright, so let's start with the introduction to DOTS. So first of all, why do we need it? Because, you know, this is kind of a new technology for us, and definitely it has some learning curve to it. So why do you need it? And the very short answer is performance. Let me start with the chart. Let's take a look at this chart, and you can see how over the years performance of the processors was increasing. Every year we had almost double the performance, but on the other hand, the memory, it didn't quite catch up with the processor performance, and year by year the gap between processor and memory performance is actually increasing. And this is going to play a huge role in how efficiently we can process data in our simulation or our game. If you want to perform any operation on your CPU, on your processor, you need to load your data into the registers. When the data is in the register, it takes basically 0 cycles to start performing operations on that data. Of course, different operations like, you know, multiplication, division, maybe some math stuff like sine, cosine is going to take different amount of CPU cycles, but just to get the data, when the data is already in the registers, you don't waste any more time for getting this data. When your data is residing in the level 1 cache, it takes roughly 3 cycles to get it to your registers. From L2 cache is around 20 cycles, and main memory is around 200 cycles that you waste basically on waiting for your data to be loaded into registers. And it's really hard to get intuition on that. That's why I think this would be very good visual representation of what is happening. All right, so now I'm going to click, and there will be a white rectangle going from here to the processor, and make sure you don't blink because this is going to happen very fast. All right. Okay, so this was the time that it would take to load data from the level 1 cache. Now level 2 cache. You can see it was a little bit slower. And now if you want to load data from your main memory, you can see that this is way slower. So it's a situation that we try to avoid. We want to operate in this area. Sorry. We want to operate in this area. We want to have our data in the cache closer to the register, so we don't waste any time loading, or at least we want to avoid loading data from the main memory because it's way slower. So this is a very common scenario. So here we go through a list of our game objects. In this example, this is a bird. So for each bird, we want to move it in a certain direction, giving it a delta time. Okay, so what will happen is that in the move function, we're just iterating here and adding x, y, and z values according to our input. And you can see here that data is usually read with the 64-byte cache lines, and it's kind of here conceptually split into 8-byte chunks, so it's easier to understand it visually. And here is how the 56 bytes of birds look like in when loaded into your memory. And here are the bird's position. So this is the part that we are actually going to work with. This position is here, vector 3. And what you can notice is that we are wasting here around 80% of the memory, right? We load so much because our CPUs, when they load stuff into your cache, they use the 64-byte cache lines, but the relevant data, it's only a small portion of that. So we can improve it by doing this. So here you can see that I have a very similar scenario. So I'm loading 64 bytes cache lines, but here my data is really tightly packed. So my positions in the memory are laid out right next to each other, so that when our cache line is loaded into the cache and then later into the registers, the relevant positions of these game objects are right next to each other. So the previous example, you might hear that it's an array of structures, and this particular one, it's the structure of arrays, and this is exactly what components do in our ECS simulation. They make all the data that goes into your CPU cache very tightly packed, so we can perform operations much faster. There are also these concepts of locality reference, spatial locality and temporal locality. And spatial locality basically means that if the memory address is accessed by a program, then it's very likely that address is right next to it. So if, let's say, you had address n, then n+1 and n+2 are very likely to be also accessed. And iterating sequentially through this kind of data stored in array, for example, is going to have a high degree of spatial locality. And then we have the temporal locality. So if memory address n is accessed by a program, then it's very likely that we're going to access this again in the future. That's why we have this CPU caching. All right, back to the dots. So here you can see that data-oriented technology stack, or DOTS, has many different systems to it. And there's entities, there is C# job system, burst compiler, Unity physics, netcode, and all these different packages. Most of the time they are delivered as a package through the package manager. Most of them now are in a preview, some of them are experimental. So keep in mind, if when you go into production, most of the time you don't want to use the preview packages, but if you want to experiment with some of these packages, or maybe are sure that it works for your project, why not? Today I'm going to focus mostly on the entities. Okay, so this is one of the packages, and all the examples I'm going to provide are going to be executed on my Unity 2020.1. This is a beta version, and also I think it's the newest one, at least from what I know. This is 0.11 preview 7 as of today. This is the newest one. Alright, so entities and ECS. So ECS stands for the Entity Component System. Okay, and entity, I think the closest comparison to what we have in a mono behavior is a game object, but it's not an actual object. It's more of an abstract. In the abstract thinking, I think of it as a game object, but it's not an object. It's rather an ID, and this ID, the entity represents this individual things in your simulation. Then you have your actual data, which is components, and they basically represent all the data associated with different entities. And finally, we have systems that basically allow you to create behaviors. Okay, so systems, they take data from the components and they transform it to new states. So for example, this could be moving or rotating your objects. We also have a concept of an archetype. So here you can see that I have 3 different entities, and this archetype, it's a unique combination of component types. So for example, a 3D object can have a component that is world transform, the other one is linear movement or rotation, and each of the instances of these 3D objects, they correspond to one single entity. And because they share the same sets of components, like here, translation, rotation, lookout toward the renderer, ECS classifies them as a single archetype. Next, the archetype of an entity determines where the ECS stores the components of that entity, and ECS allocates this memory in chunks. So you can see it here. For each archetype, we have the chunks, and each one is represented by an archetype chunk object. And the chunk always contains entities of a single archetype, and when one of the chunks is full, it's going to allocate a new chunk of memory. If you, let's say, remove a component, so let's say I remove my component here, this is going to become a different chunk. And finally systems, they operate on these entities in chunks. So basically, when you have one set of entities coming with different components, your system is going to either read or write to them and perform some operations, right? So we can think of a system as a way of processing your data from one state to another. Okay, and I'm going to start with the first real life example. I'm going to walk you through creating the most basic, most simple, the simplest possible example. So this will be a bunch of rotating cubes, and to achieve that in ECS, I'm going to need a component. So it's this one here. I'm going to need an authoring script, and I'm going to need a system. Okay, so you can see before I jump into Unity, the components, they are actually structs that most of the time inherit from iComponent data, and all the data that you need later in a simulation is going to be a public field. So here I have only one piece of data, which is my rotation speed, so I just named it the value here. Now we will need a way of creating these entities. So I'm going to convert my game object in my scene from a game object to entity using this authoring component. And I'm going to, in my mono behavior, you can see that this one is mono behavior. I'm going to expose this parameter, my rotation speed, and then because this one is implementing the iConvert game object to entity, I need to implement this method here, convert. That's going to provide me with the entity manager for my destination world, and with that and the reference to my entity, so once my game object is converted to the entity, I can add certain components to it. So I'm going to add this rotation speed here. And finally, I'll need a system. So the system is going to first on update, I'm going to implement this method here on update. And on each update, I'm going to grab the delta time. All right, and I'm going to create a new job inside my system. And this job is going to be for each. Here I need to pass different components I'm going to use. You can see that I have ref and in. In basically means that it's on read only. I can't modify whatever is coming here. Ref means that if I modify the rotation value, it's going to save it and maintain that modified value. And this for each, it serves kind of like a filter. So I could add different components here, and this will basically automatically filter all different entities in my scene and provide me with the reference in this loop here. So for each entity that has rotation and rotation speed, I'm going to perform this operation. I'm going to get the rotation and make it multiplied by this one. So this will be in Euler angle 0, my rotation speed value times delta time 0, and I'm going to schedule it to run to basically run this job. Okay, so time for a demo. So here you can see that I'm going to create a new 3D game object. It's going to be a cube, and I'm going to give it a new material, just a simple blue material. All right, so this is my cube, and first I'm going to do a simple rotating cube in mono behavior. So I already have here let's change the name to MB, like mono behavior, and I'm going to add a component called rotate cube MB. And if you take a look here, this component is basically here I have the rotation speed, which is 10, and in my update I'm just rotating around the y-axis. So when I press play, it should slowly rotate 10 degrees per second. I can't see it because the position is off, so I'm going to fix the position here and play again, and hopefully what should happen is that it rotates 10 degrees per second in the clockwise direction. So this is fine, but if you want to scale it, I'm going to turn it into the prefab. If you want to scale it and instantiate hundreds or thousands of game objects, this is going to cause some problems. So here I'm creating a new script, instantiate mono behavior, that's going to instantiate many prefabs into my scene. So I'm going to start with 10 by 10 by 10. So here you can see that for each of these values I'm going to instantiate one prefab. What will happen is that I will have 1000 rotating cubes in my scene. and you can see that this is actually fine in my profiler. Let's come back to here. You can see that the behavior update takes roughly 3 milliseconds, and this is not horribly bad, but if you think about it, it's only 1000 rotating cubes, nothing else. All right, so if I try to scale it even further, let's say I want to do 20 by 20 by 20. So this would be roughly 8000 rotating cubes. You can see that my performance actually dropped quite significantly. Right now I'm spending almost 6 milliseconds just doing this simple calculation of rotating the cubes. If I do 40 by 40 by 20, so this is roughly 32,000, it's going to drop quite significantly again, and now I'm below 30 frames per second. I'm actually closer to 15 frames per second, and this is really not good, right? Because it's a very simple simulation, and we are wasting quite a lot of time on this rotation on our CPU. So I'm going to show you how to improve performance, how to create very efficient cube rotation using the ECS. So here I'm going to first remove this one here from my scene, and I'm going to create a new cube. So 3D object, cube, assign my material to it. Drag and drop right here, and I'm going to first try to convert it into an entity, and to do that I need to add a component called convert to entity, and there are two settings: convert and destroy or convert and inject. I'm going to try the second one first. You can see when I press play and I come back to my scene view, something weird will happen. So if I move my game object, you can see that now I have two. One is selectable, I can move it around, but the second one I can't actually move it. If I go to this window entity debugger, this is kind of like a hierarchy view for your entities. You can see that the cube is there. If I do convert and destroy, you can see that my game object actually disappeared, and now I can't even select. I can select this cube. It's because this one was converted with all these default components like transform, translation, and rotation, and was moved to the entity. It was basically it's now an entity. It's not a game object. Okay, so now I'm going to add some ECS components. If you right click, go to create ECS, there's some pre-made templates. So I'm going to start with the runtime component, and I'm going to name it rotation speed. And this rotation speed is going to hold data about how fast I want to rotate. You can see that there is a bunch of nice comments created for you, so you can easier reason what this component is doing. I'm going to add a new public float value, which is effectively my rotation speed. Now let's try to add this component to my cube. If I just try to drag and drop it, you can see that it's not possible. I will need to, I can't add this component yet. I need to create an authoring component. So if I go to create ECS authoring component type, and now I'm going to name it rotation authoring. Let's open it in my Visual Studio. Here you can see that it's the thing I show you in my presentation. So I'm going to add new public float. This is going to be my rotation speed. Rotation speed, and inside my convert method, I'm going to use this destination DST manager. I'm going to use this entity manager, DST manager, to add component of the type I want. And in this example, it's going to be my rotation speed, right? So first I provide a reference to my entity, and then my rotation speed, and I need to assign a value to it. So my value is the reference I created here to my my rotation speed. Okay, I have an error here, and this is because I have to call the add component data, not add component chunk. All right, so this is fine. And now on my cube, if I go ahead and add this component, so rotation offering, you can see that the rotation speed is exposed there. And hopefully what should happen is that I'll get in my entity debugger on my cube, you can see that I have a new component on my entity, the rotation speed, with the correct value. Now what I will have to do is to create first I'm going to show you different ways of converting your game object to entities. So another one would be let's create a new system for rotation first. So I created a new rotation system, and if I go back to the Visual Studio, you can see that I have my own update method inside the rotation system, and that's inheriting from the system base. And again, we have a lot of nice comments. So if you're not familiar with ECS, you can just try to read the comment, and for me, I just uncommented the delta time because this is something I use very often. And here in my entities for each, I need to iterate over rotation, and the rotation is something I need to get the reference of, and my in parameter is going to be my rotation speed. So I just change these two. I get a reference to my rotation, and the rotation speed has the in parameter to it. Okay, so rotation speed here. And in the end here, what I'm going to do, I'm going to say my rotation dot value is going to be equal to math. This math comes from Unity mathematics. I included it there. So math dot mul, like multiply, rotation dot value, and I'm going to provide my rotation here. So this is going to be quaternion. And this one is also from the Unity mathematics, quaternion Euler, and here I need to provide my x, y, and z. So y is going to be my math dot radians, because this Euler angles is actually operates on radians, so I need to convert them to radians. My rotation speed value, z component is 0. And finally, I'm going to save it and see if this works. So what should happen? What should happen is that my cube should start to rotate now when I press play. Oh, and you can see that it's way too fast. And this is because I forgot the delta time. So I cached it here, and I need to multiply it here. Now when I press play, you can see that it slowly rotates and everything works fine. I have my rotation system here, and it's successfully rotating my... You see that the rotation value is changing here. It's successfully rotating my cube. Okay, now I'm going to show you how you can avoid the so if I add this generating offering component to my iComponent data, I actually don't need this offering component, and I can just drag and drop my iComponent data here, and it's going to work very similar to what I achieved with my rotation offering, and the result is exactly the same. So this is just a nice thing that you can use to avoid creating this new script, rotation offering. Now I'm going to show you a second way of actually preferred way of creating your entities. I'm going to right click and go to new subscene from selection, and I'm going to convert convert my entity into to move it into the subscene, right? So now I don't need this convert to entity component. The subscene is the thing that manages and converts my game object to an entity. And hopefully what should happen is when I press play, it works exactly the same. If you want to modify your subscene, you can press this checkbox. If you are done with modifying it, you can uncheck it. And the nice thing about it is that if you go to the entity debugger, it will show you all these entities coming from the subscene in your list in the entity debugger. All right. I'm going to remove it and recreate my cube again. Assign a material to it, rotation speed. Alright, the default value should be 10. Assign material to it, and I'm going to turn it into a prefab. And I'm going to write a new script that's going to instantiate all as many cubes as I want. So here I'm going to create a new script. It's going to be a new create C# script, and I'm going to name it instantiate ECS. And it's going to be very, very similar to what I had with my mono behavior. So if I find it here, instantiate mono behavior, I'm just going to copy all of that and move it into my instantiate ECS. Okay, but I need a few more things here. So first, I will need a reference to my entity when I convert it from game object to entity. And to that, I will need to add using Unity-ANZSEA, this namespace here, and mathematics. I think I'll need that too. And here I'm going to manually convert it. So I'm going to call game object conversion utility dot convert game object hierarchy, and I'm going to say convert my prefab with these settings here. So my settings are going to be, I need to provide a destination world. So let's just assign it to a variable here. World is equal to world dot default game object in injection world, and I'm going to pass it here. I'm going to leave the flags as 0. And here what I also need is my entity manager. So I'm going to go ahead and create a new entity manager from my world.entityManager, just like that. And here, instead of instantiating my game object, I'm going to use entity manager to do that for me. First, let's figure out what's the actual position I'm going to spawn my object at. It's exactly the same like I had before. So x times distance, y times distance, and z times distance. And here, finally, I'm going to call entity manager dot instantiate. This is going to be reference to my entity that I just converted, entity like that, and I'm going to assign it to a variable. So it's going to be my new cube variable, and I'm also going to use the entity manager again to set some component data on it, and it's going to be the position. And of course I'm going to comment this one out because I'm not instantiating a game object. And of course I tried here to pass just my float free. I actually need to create the translation, so I'll also need using Unity.transforms to get a reference to my translation here. So new translation, just like that, and the value is going to be equal to my position. Okay, so now the boring part is done. and let's see how many we can actually instantiate and move around my scene. So now if we add this instantiate ECS component and assign a prefab to it, you can see that I can easily instantiate 1000 objects, and it's not a problem, at all. And you can see that it's not actually taking that much time. It's way less than 1 millisecond. So I'll try to increase that number to maybe 40 by 40 by 20. That was the number that mono behavior couldn't cope with. And here you can see that it's actually not that much either here. So I'm way above 200 FPS. I could pump this number up into 50 by 50 by 50. Maybe let's start with 20. So this is way more than I had before, and I'm still way above 200 milliseconds. You can see in my profiler that most of the time is actually spent on rendering my cubes than actually performing the rotation. I'm still over 100 FPS. I could try to increase it even further. 100 by 50 by 50. And right now I'm at steady 60 FPS. And you can see that most of the time is spent actually on presentation system group. So it means that it's not the rotation that's taking so much time, because the actual rotation is 0.04 millisecond. It's the actual rendering that's a bottleneck here. Okay, so let's add a little bit more complexity to that. On top of the... what is that? On top of the... what we have here, I'm going to add a new system that's going to move the cube forward before I actually rotate it. So I'm going to create a new system, move forward system, and let's inspect it here in my Visual Studio. And it's going to be super simple. I'm actually going to just uncomment this float delta time here. It's exactly the same as before. And here I'm just going to uncomment this one here, translation.value plus equals the forward direction based on the rotation. Alright, so now when I press play, they should both rotate and move forward. Let's see. So this is how it looks like in my scene view. And so now I have two systems, rotation system and move forward system. What if I want my move forward system to be executed before my rotation system? There's actually a attribute that you can set. So on my move forward system, I'm going to add this update before, and here I can pass a type to a different system I want to be updated after. So now the move forward system should be updated before my rotate. So let's see if it works. In my entity debugger, you can see that now move forward system is being executed before the actual rotation, and we have this crazy huge amount of cubes that is moving and rotating. And actually we can increase that number. So I'm going to do 100 by 100 by 50. So this is roughly 500,000. 500,000, and you can see that I still have steady 30 FPS, and it's moving and rotating at just a fraction of a millisecond to perform this operation. So just think about how much performance gain did we got here. The previous one using mono behavior was taking like 16 milliseconds to calculate the rotations, but here it's less than 1 millisecond, and the actual bottleneck is rendering, not performing operation on the data. So the data that I used just now was the iComponent data. We still have quite a few different types of component data: shared component data, system state, iBuffer, element data. iBuffer is very useful when you want to reference some dynamic, let's say, lists or arrays. But today I want to focus mainly on the iComponent data and shared component data because they are very powerful and can actually create quite a nice features with that. So let's move to the next section, the steering agents. So I implemented the steering agents scene here, and what it's doing is basically I'm able to select these entities here, and when I click somewhere, it's basically telling them, hey, please move to this target position, and I can do this one by one. So effectively what is happening here, I'm grabbing each one of these entities, and there is a component on them, target position, and I'm setting this target position to somewhere where I click in the world. Okay, and this is the actual component data that I was using. There's the steering agent with the target position. There is a velocity component to it. So the most important components that we are having is the translation, rotation, velocity, and the steering agent with his target position. So what I was doing just in my scene, I was setting the target position here. Okay, and then later this target position, after we set it, it was used in the steering system to figure out what is the target velocity based on the position and the target position and the current position. Then the steering system is going to figure out what's my velocity, and with that velocity, finally I'm going to execute this move system that's going to just move it according to this velocity. So my steering system is right here. I added this update before move system because I wanted this happen first. Again, I'm overriding my own update. I'm caching some data here. So this is my maximum speed, my slowing distance, and delta time. And now here for each of the entities that have velocity, translation, and the steering agent components on them, I'm going to calculate. So from the position where I clicked on my screen, I have my agent here. I'll calculate this target offset. So this one here. I get the distance. I can calculate the ramp speed. So I divide it here by the slowing distance. So when my agent gets closer to the target, and this is below the slowing distance, he's actually going to start to slow down. So when he arrives to the target, his velocity should be 0. Then I calculate my steering velocity based on my target speed divided by distance. I added this very small value here to avoid division by 0. Multiply by target offset and minus equals the current velocity. And with this steering velocity, right, so this will be probably facing somewhere here, I calculate the final velocity, which will be facing towards the target. And finally, I have this move system that's updated after the steering system, and this one is even simpler because it's just taking, actually should convert this one to in, but it's basically taking the reference to the translation, rotation, and velocity, and I'm basically just moving forward according to whatever velocity I had. And I'm also, I need a reference to rotation because here I'm basically rotating every single steering agent. So if my velocity is here. Okay, I'm going to rotate my agent according to the direction of the velocity. Okay, and based on that, I built this formation movement system. So the inspiration was the ancient formations that you had in Roman legionaries, right? So I just took these 3 formations. The first one is called the tortoise, and basically it means that all these soldiers, they are moving on a grid right next to each other. The second one is the orb formation, where they are moving like in a circle, and the wedge formation right here. So let's start with the taking a look at these components that we are going to need to perform this formation movement. And you can see that I have quite a few, and I'm going to show you the visual representation for that. I'm going to have one formation leader that's going to basically tell all the following soldiers where they should go. And this one, it has standard, just like before, translation and rotation, and velocity and steering agent from my steering and move systems. So this is just like the basic steering agent, where I was telling him to move into different places. But on top of that, I have this formation leader component, and the formation leader, it has an ID, okay, and that's it. So I have this formation leader with an ID, and now each of the soldiers, they also have all this translation, rotation, velocity, steering agent right here. So this is exactly the same, but then each one of them will have to have one of the 3: the tortoise, orb, or wedge formation, the formation index. So formation index will hold a reference to what is his number in the formation and what is the total number of soldiers in that formation. Okay, so this is the formation index, and then the formation group is going to hold the ID to the leader. Okay, so the formation group is actually a thing that will tell him, hey, I actually belong to this formation leader, and I'm going to follow this guy instead of any other formation leader that I have. Later, I'm also going to add this health component that's going to be used when I shoot projectiles and try to destroy these formation soldiers. So based on this testudo basically means tortoise in Latin. Based on this testudo, orb, or wedge formation, I'm going to have 3 different systems that are going to basically filter for either of these testudo formation component, orb formation component, or wedge formation component. And based on that, they are going to give it a target position. Then I'm going to write a system aligned with leader that's basically going to take this relative, let's say if it's like a tortoise formation and my leader is here, it's going to transform these rotations to be relative to the leader. And finally, I'm going to execute this steering and move systems based on the target position that was set here. I'm going to start with this testudo or tortoise formation, and you can see that it's very simple. So we basically have our soldiers in a grid, okay, and they basically have to be aligned to this leader here in the middle. This guy here is my leader. So this testudo formation system that's going to set this target position is doing something very simple. First, you remember I told you that each of these soldiers, they have the steering agent on it and the formation index. So this will be a number like 1, 2, 3, 4, and so on, until I think here I have 1, 2, 3, 4. I have around 100 or so. So the last one will be 100 or something like that. Okay, so I'm grabbing this index and I'm going to calculate first the middle position, and then I'm going to calculate the X and Z position. So this would be like here, let's say -5, and here 5 on the x-axis, and then I'm going to do exactly the same for the z-axis. And after I perform this relative position to my leader, I'm going to set on my steering agent, I'm going to set the target position just like that. And after this is done, I'm going to schedule parallel this job. Schedule parallel means that the work in this job can be divided into different worker threads. And one thing that I didn't notice yet is that before I actually schedule this for each job, I'm filtering it to allow only entities that have this testudo formation component on them. Okay, because this is this Tertis testudo formation system, so I only want this testudo formation component on my entities. The second one is the orb formation. So with the orb formation, I put my leader here in the middle, and I try to arrange them in a circle-like formation. And I can do this again by creating this orb formation system that's filtering for orb formation component on my soldiers here. And for each steering agent, again, I'm grabbing the formation index that has the actual index, so this will be like 1, 2, 3, 4, and so on until 10. And I also have the formation count. So based on that, I know that I have 10 guys. Let's say this one is index 1. I'm going to calculate what is the radius based on that, because I need to maintain a certain distance between them, right? So then I know that in a circle I have 2 pi r. This is the circumference of the circle. So I need to calculate what is the radius based on the distance I have and the number of entities. I also cache the 2 pi here, and based on the radius, I can also calculate, like, if it's index 1 and I have 10 entities altogether, I know that I have 2 pi radians on my circle. Okay, so the only thing I need to do, I need to multiply my 2 pi by my index, so this would be 1 over 10. So then I can get nice angle here for each of my entities. Okay, and in the end I just set the target position here. Finally, the wedge formation, also very, very similar. So I have my leader here in the central position, and I basically start placing them here: 1, 2, 3, 4, 5, 6, and so on and so on. So again, this is a separate system, wedge formation system, that's filtering and getting all the entities with the wedge formation component. I have a steering agent and the formation index, and again, the calculation is super simple. I just try to figure out the relative position here. Finally, once this is done, this will give me only the relative position to the leader. I also need a absolute position in the world. So I'm going to show it this in a while. But first, when I instantiate my soldiers, I'm using a little bit more efficient method. So instead of instantiate them one by one, I can actually create a native array with a number of the soldiers I want to instantiate. Okay, and I can call my entity manager instantiate. Here I'm going to pass my prefab and the reference to the native array. So the native array has, let's say, 100 soldiers in it. So I'm going to instantiate 100 at the same time by calling this entity manager instantiate. Then I'm going to pass the position I want them to instantiate at. I'm going to pass a reference to the leader they're going to follow. And for each one of these soldiers, I actually need to set some components like the formation type, what's his current target position, the formation index, right? So this is the one I took just now. So when we iterate through all the soldiers from, let's say, 0 to 100, I'm going to store the index here, and also the count of all the soldiers together, and the formation group. So this is the shared component that I'm going to use later to find the relative position to my leader. Okay, and I'm going to show it to you how I use this one in my align with leader system. Okay, so first I will need to get a reference to all the leaders I have in my simulation. So this is this part here. I need to create a query that will query all the entities in the world. I'm just going to read them, so it's read only. I'm looking for translation, rotation, and the formation leader, right? And with that, I will, on update, I'll basically get all my leaders from the query. I'm going to create like a native array here with my formation leaders, and the same for the translation and rotation of this formation leader. And now this bit is really important, because now you remember my formation group. The formation group was holding information about the leader ID. Okay, and I'm basically getting, with my entity manager, I'm calling get all unique shared component data. So it's going to give me groups that have the same leader ID. All right, so here, after I call this formation groups passed into the get unique shared component data, I'll get a list of all different groups with different leader IDs. All right, so now once I have this group, I can iterate through each one of the leaders, and I can get the one that has his ID matching my leader ID, right? So here, here when I iterate for each formation group, I'm checking if the leader ID of the formation group is exactly the same as the leader I'm iterating through. All right, and I also store his position and rotation. And now this part is important. So because I was iterating here for each, I was iterating through each of the formation groups, I can pass it as a filter to my entities for each, right? So here, before I call for each, I can actually add a filter, so I'll iterate only through the formation group that is matching my leader ID here. Okay, and this way I can get my steering agent, right? You remember here the target position, and I can change this target position from relative to the leader. I can make it absolute position in the world. So if let's say if my leader is rotated by 180 degrees, I'll first rotate all of them by 180 degrees and also add the leader position. So this way I get the absolute position in the world. All right, so now it's time for the demo. I'm going to switch to my Unity. And when I press play, you should see that, basically I can select one of the leaders, and if I click, all different soldiers will basically follow him, and use the steering agents to calculate the target velocity and move according to that velocity. I also added a system that allows to switch between different formations. So this effectively will remove and add the testudo, orb, or wedge formation components. All right, and this is actually very effective. So I could increase the number to I have maybe 90,000 in one formation. I try to keep this number low because although it's very performant, and you can see that I still have like very, very solid performance. I have well over 100 FPS with 90,000 dynamic agents, but it just doesn't look good and it takes forever for them to align. So I'm going to switch back to just 900 soldiers per one formation. And something that I also added later is I added this projectile spawning system. So basically now when I press space, I'm going to spawn how many? I'm going to spawn 60 by 30. I'm going to spawn almost 2,000 bullets. Bullets is 1,800 bullets. It's not using Unity physics. It's actually using separate system that I created. So I'm basically giving a velocity to my bullets, and on each iteration of the system I'm checking the collision with agents against the bullets. So let me show you that, because that collision system is interesting. Probably if you create a system like this for yourself, you should probably use Unity physics, because it's already there and it's working quite well actually. But this collision system I created here is something also very educational. So instead of using the actual physics, you can kind of fake the collision. So here, before I execute my move system, what I'm doing is I create a new collision job, right? So I'm creating this job myself, and I also add this archetype chunk component type for the health and translation. So this is basically the position. And on each execute, right, for each execute for my archetype chunk, I'm getting the native array for my health and position. All right, and here for each thing that resides in my chunk, I get the health and position, and then I test the collision against this native array that I have here. And this native array is passed to the job from the onUpdate. So here, inside my collision system, I have two queries. One is querying for the soldiers, one is querying for the projectiles. So when I query for soldiers, I'm looking for the health component and the translation. When I query for my projectile, I'm querying for the projectile time to live, because I gave them like 5 seconds to live before I destroy them, and the translation, which is the position, right? And here on update, I'm basically creating this job, and I'm assigning some stuff to it, like this health type and translation type, by getting these archetype chunk types and getting my projectiles as a native array. All right, so then I'm going to show you the culling system. So here I'm basically giving a damage to each of the soldiers, and when the health decreases, if it's equal to 0 or less than 0, then I'm going to destroy it. And there's a culling system that I'm going to show you that's handling that. Yeah, so this is the formation system you can create using the shared component data and this steering agent's behavior. So remember, they know which leader they should follow, because each of these single soldiers, they have the formation group that's holding the ID of the leader, right? So later in the job we can filter based on the leader ID. And one thing to note is that when I shoot all of them and I want to destroy them, it's not very efficient to perform this kind of operations on the main thread. Okay, so this is something I want to avoid. And what I'm doing here is I'm deferring. You should always try to defer removing components, removing entities, and performing all these structural changes to your simulation. You should defer it, and you should do this after all of this, after all your system are executed. Then there is a right time to perform the structural changes, because otherwise, if I would remove my entities somewhere here or here, it's going to basically invalidate some of the data that's being executed here, and it's going to create sync points, and it's going to slow down the entire thing. So to perform the structural changes, like creating entities, deleting, adding components, removing components, or changing the value of the shared components, we can do all of that here. After all my systems are executed, there's this end simulation entity command buffer system. Okay, so I'm going to use this command buffer to remove my entities. And you can see I have this culling system that I created, and I'm going to keep the reference to this end simulation entity command buffer when on create. So this is when my system starts. On create, I'm getting it by calling my world get on create system and simulation entity command buffer, and then on my update, I'm basically checking. First I create this command buffer, so I'm calling end simulation entity command buffer system create command buffer to concurrent, so it's running on multiple threads. I'm creating and storing it here in the ECB variable, and for each of my entities that has time to live component, I'm basically decreasing the time to live based on the delta time. When this one goes below or is equal to 0, then instead of destroying it right away, I'm calling my entity command buffer destroy entity, and I'm also passing the query index and the reference to the entity ID. And the same for the ones with the health. So each soldier with the health, here I'm iterating through all of them based on this health reference here. It's actually could be in instead of ref, because I'm not modifying this value. So for each of these soldiers with the health component, I'm going to check if the health value is less or equal to 0, and based on that I'm going to call my entity command buffer and destroy entity. Okay, so using this entity command buffer, I'm not performing these structural changes right away. I defer them to be executed at the end of my simulation with the command buffer. And one important thing to remember is that you should also write this guy here. So you also want to add the job handle for the producer. Don't forget about adding this one. Okay, so now I think I'm going to go through the Q&A. Where can we find the project files? So if you are interested in project files, I'm probably going to share the entire project on Discord. So here you can see we have a Discord channel for Unity, Southeast Asia and Australia, New Zealand. And this link will bring you to the channel that's going to be used as a post-webinar Q&A section. So if you have any questions that you couldn't ask me today, or maybe I'm not sure when I will share the project files. I need to clean up the project a little bit. If I post the project files anywhere, I'm going to post them here. is the visual scripting workflow going to be available for dots? So if you go to the forums, I'm going to share the link to the forums. If you go to the forums, you can check out there was a preview experimental drop of the visual scripting system for dots, and this is something you can check out on the forums. Is ECS supported on all platforms, including WebGL? So I think it should be supported on most platforms, but I'm not sure about WebGL, because WebGL is always a little bit special. Because, for example, if you build now for WebGL, you don't have multi-threading, right? Everything is a single thread, so this is a huge limitation, and I'm not sure if it's supported on WebGL. I don't think it's supported on WebGL now. All right, we kind of run over time, so it was supposed to take only 1 hour. So I'm going to, if you have any more questions, please join the Discord channel, and I'm going to answer all the questions on Discord. But for now, I'm going to show you some useful links that I think, if you want to start developing using ECS, these are the links that would definitely be useful. So first, the documentation. When I was preparing for today's webinar, I used the documentation a lot because I think it's pretty solid and is getting updated with each release of the entities. So I was using the latest manual from the documentation. There's also a playlist for Unite talks on YouTube from the Unite Copenhagen last year. And you can find, I think there's well over 10 videos that are very, very useful. So please do check out YouTube videos from Unite Copenhagen. And of course, because this is a preview feature, if you have any issues, you should probably go to forums and try to seek help on forums, because this is a place where you're going to get a response from people who actually work on a feature and develop ECS and entities. So definitely you should check out the Unity forums. And before I finish, it would be really great if you can take 1 minute to fill in the survey. So you can either scan the QR code or use this link. We are still experimenting with the format of this webinar, so if you have any suggestions, please do let me know in the survey forum. Let me just quickly look at the Q&A section. So another question I got is, for systems, can we set which systems to run and which to disable? So yes, there's an API that allows you to enable and disable systems. You can actually make the system not being run automatically. So it's not going, because all the systems, you could notice that I didn't start them manually. I didn't call like, hey, my move system .start. Nothing like this happens. They were actually started at the moment when I created them. So once I have the C# script in my project, the system is going to start automatically. Is there a dots editor? What's the status of Project Tiny? So Project Tiny is, I think the package is already available. And you should be able to get it from the package manager. And the proper name for Unity Tiny now in the package manager, I think it's dots runtime. So I can look for the dots runtime and or the Utiny. And from what I remember, there is already a it exists in a package manager. So is dots something you only need to implement when you're having performance issues in a game or due to the structure and setup of the engine. It is something that should be thought of before you start your game. So I think DOTS is really great when you want to improve performance in your game. And we saw some studios that implement the entire game logic in ECS, and this is fine. It's going to be a little bit more difficult because we are all used to programming our games with mono behaviors, right? So it might be a little bit difficult for you to switch in thinking in ECS pattern, entities, and dots. But of course, you can create like maybe very demanding simulation that's running on your CPU. You can make it implemented in dots, and the main logic of the game can still be using the mono behavior. All right, so I think that's it for today. Thank you very much for joining, and again, if you have any more questions, please join us on Discord, and there'll be a post-webinar discussion there. Thank you very much for today, and see you on the next webinar.